I'll share my screen one more time. So remember on Wednesday, we started talking about kind of this idea of finding areas underneath of functions. If you didn't pick up that that's kind of the point of what we were doing here. So we started talking about it in terms of distance with the velocity function, but the distance turned out to be that area underneath the graphs we were looking at. And that was kind of the point, is that we're not just going to look at this in terms of distance and velocity, we're also going to transfer it over to more generic situations. And essentially the thing that we want to do is we want to end up finding these areas underneath of these functions. But then remember, we ended with kind of this idea that we're going to start with which is you don't always have a nice graph to find the area of. Sometimes it's a shape that you don't know the area of. So remember, I said we're going to split these up into kind of sections, and we're going to make a rectangle in each section. So then we're going to be able to estimate the area by just adding up the areas of all the rectangles that we have. And also remember that we're going to have essentially two choices. So if we split this graph up into a bunch of different sections, we know that the width of the rectangle is going to be however large that section we're taking is. But then to figure out the height of the rectangle, we kind of have choices because we have the function takes different values in that section. So while you could technically pick any value you want, we're going to do two. We're always going to choose between one or two different options. We're either going to take the value of the function at the rightmost point or the leftmost point of that interval. So that was kind of what we were building up to the other day. We didn't get to any official examples. Also, before I forget, these are called Riemann sums. Wait, does the E come first? I always forget which way his name is spelled. It's a guy's name, so I can't remember if the E comes first or the I comes first, but it's a Riemann sum. So if you hear me say Riemann sum, this is what I'm talking about. I'm talking about taking these rectangles and adding up all of their areas. So let's get into our first official example. Right, I always forget that I gotta turn the pen off to be able to scroll down. There we go. Let me try to leave that in a little bit. No, I don't have the space. So suppose a car is moving with increasing velocity, and that we measure the car's velocity every 2 seconds, and that gives us the data in this table, and we want to estimate the distance traveled in that 10 seconds. So here we're still doing it in terms of velocity. So if we could graph this velocity curve, we would want the area underneath of it. Now to try to demonstrate this in a picture, I'm going to draw the graph of this very roughly. I'm not going to try to make it perfect, but just to give us an idea of what the rectangles we're going to take are going to be. The lag is partially real. There we go. So I have to go through up to 10 on the t-axis. So let's go by 2s, since that is what this goes by. So 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. And I have to get all the way up to 50. So why don't we go by 10s? 10s, 20, 30, 40, 50. And say I wanted to take those kind of coordinate points and I wanted to graph them to get an idea of what the shape of the graph will look like. You don't need to do this for these table examples. I'm just trying to make it very clear what we're trying to do here. So we're going to do another one in a few minutes, another table example, and I won't draw the graph for that one. So you don't need to draw the graph for these, but I think it'll help demonstrate what we're doing since this is our first official example. So we have 0, 20, 2, 30, 4, 38. So, just put them to the best of my ability on here. 44, 48, and 50. So we've got that the velocity function, looks maybe something like that. So we want to estimate the area underneath of this function. Why did I say 8, 9? That should be 8, 10 on the t-axis. And we want to stop at 10. And again, that's not a shape that we know. It's not quite a triangle. It's not quite a quarter of a circle. It's not quite a trapezoid. It's nothing that we know the actual area of. So we're going to have to estimate the area using our rectangles. So now, since they give us this table and it's in terms of, 2, and they don't tell us. So go back up a little bit. With these, sometimes they'll tell you kind of how to form your rectangles, and sometimes they won't. If they don't tell you, then it must have been a table. Sometimes we'll have ones where it has a function and they need to tell us how to form them in that case. But anyway, in this case, since they don't tell us how to form the rectangles in any way, and hopefully you'll see what I mean when we do one of the examples that it does tell us, since they don't specify, let the width of the rectangle be, I don't know, 1 or 4 or whatever width they would want the rectangles to be. That's usually what they'll specify, is they'll specify how wide they want the rectangles to be. So then you split up that entire interval into that many pieces based off of that width. But they don't specify that here. So since we're given a table that's broken up into kind of pieces of 2, 0 to 2, 2 to 4, 4 to 6, and so on, we're going to take the width of our rectangles to be 2. So we're essentially going to break this up in kind of, at every single point, essentially. So we're going to break this graph up into those 5 pieces. Now those 5 pieces should be of equal width. That last one looks a little skinny, but that's just because I drew it poorly. So, 2 things that I should say before I forget. Actually, I'll say that in a second, but I'll write this over here so that I don't forget to talk about them. So I'll talk about this in a second. But essentially what we're going to do here is, remember, we have 2 choices. We can take the right side or the left side. So let's actually find both here. So we're going to find a right-hand sum, which is what that would be called. Right. Can I spell right correctly? Right-hand sum. And then we'll find a left-hand sum as well. And I'll try to use some colors here to make it understandable what we're doing here. So if I want to do a right-hand sum, that the y value that I'm taking to be essentially the length of my rectangle is going to be the y value of the graph on the right side of each one of these intervals. So if you think about how we just broke up this graph, we have essentially this interval from 0 to 2, this interval from 2 to 4, this interval from 4 to 6, from 6 to 8, and from 8 to 10. So if we want to use the right-hand sum, we're going to use the y values at all the right endpoints. So we're going to use the y value at 2, the y value at 4, the y value at 6, the y value at 8, and the y value at 10. So essentially every single y value except that first one of 0. So essentially what that would break this up, and if I want to draw the rectangles here, we'd essentially have a rectangle that has a height of 30 in that first piece, a height of 38 in the second piece, a height of 44 in the third, 48 in the fourth, and 50 in the fifth. And I'm getting those numbers from the table. I didn't just magically pull them out of the air. So essentially for this right-hand sum, we're essentially using all of these values on the table, the 30 through the 50. Now, again, what you want to think of is we have rectangles here, so we want to add up all of the areas of those rectangles. Each one of those rectangles is going to have a width of 2, because again, we're going from 0 to 2, and then 2 to 4, and then 4 to 6, and so on. So each one of these rectangles is going to have a width of 2. So if I wanted to start writing out the areas of these rectangles, let me just label these as numbers. So the first rectangle, rectangle 1, has a width of 2 and a height of essentially f of 2, if you will, which was 30. So this is rectangle 1. I'm trying to be like super, I don't know what the word I want is. I don't know. I'm trying to be like really super specific about writing things down. Our second rectangle has a width of 2 again, and the length that we decided to use was the y value at 4, which was 38. And then the third rectangle has a width of 2, and we chose the y value to be the y value at 6, because this is essentially the third interval from 4 to 6, so we take the right endpoint, so we find the y value at 6, which is 44. Fourth rectangle has a width of 2 and a height of 48. And then the fifth rectangle has a width of 2 and a height of 50. So you kind of think of it as kind of breaking it up into intervals, and then the length of the rectangle is going to come from the y value of either the left endpoint or the right endpoint or the left endpoint, depending on which sum you're taking. So if we punch that into a calculator, we would get 420. And this is a distance, so it would be in miles. Well, it's a distance specifically that we were given. No, it's not. It would be feet. Whoopsies. Because the units here are feet per second, not miles per hour. Are there questions on how I found that? I'm going to hold on a couple seconds in case someone's typing something. So we're breaking this up into a bunch of different rectangles and then just adding up the area of the rectangles. Okay. So now let's do the left-hand sum. I'll do that one in green because I think that's what I was using last time. So here what's going to change is instead of using the right endpoint for the y value, we're now using the left endpoint. So 0, 2, 4, 6, and 8. So our rectangles would look something more like the rectangle at a height of 20 for the first rectangle, and then 30 for the second rectangle, and then 38 for the third, 44 for the fourth, and 48 for the fifth. Okay. Now the widths didn't change. And well, I always just refer to the widths as the t-axis one. So the widths didn't stay. Oh my goodness. The widths didn't change. They're still 2. So the width of the first rectangle is 2, but now our height is 20 instead of 30 because we're using the y value at the left endpoint instead of the right endpoint of that interval. And then the second rectangle has a width of 2, but now we're using a height of 30 instead of 38. And so on and so forth. So the third rectangle, width of 2, we're using the y value at 4, 38. Fourth rectangle, width of 2, length of 44. Fifth rectangle has a length of 48. So essentially with this one, we're using all but the last value in the table. That's another way. It's not like the official way to think about it. You want to be a little careful thinking about it that way. But I do find that a lot of people like to think of it that way. If you plug that into a calculator, you get 360 feet. Questions, concerns on how I got that one? Okay, a couple more things before we move on. Well, to another example in a second. But notice that the right-hand sum, what about it is kind of confusing. And I could try to explain it better, or maybe it'll just click when we do some more examples. I don't know. Ooh, that's a good question, Ami. So, brain. Would both answers be okay on a test? On a test, I'll usually, well, okay. If I don't specify, you usually just have to do one of them. And if I don't specify, you would get to choose. Like if I don't tell you which one to do, that's on me and I have to accept both of them. And again, I usually only expect you to do one of them, not both of them, unless the instructions say so. So make sure you read the instructions of the problem. I might say find a right-hand sum. I might say find a left-hand sum. I might say find both. But so it's really just read the problem, see what I'm asking you. If I don't specify, you get to pick whichever one makes you happier. So Kayla, kind of the reason we have a right and a left hand is And that's kind of what I was going to babble about next. So that actually leads me into, notice that the right-hand sum, the one that I drew in blue, all of the rectangles kind of ended up above the actual function. So we have too much area in it. So so notice that there's too much area in kind of that blue one that we found. So this would be something called an overestimate. And then notice the one in green, all of the green rectangles ended up below the the function. So we didn't get enough area. So this would be an underestimate. So the reason we kind of have both is because neither one of them is perfect. And we kind of just say, well, if we take both of them, we can get an idea that, okay, well, an overestimate is 420 and an underestimate is 360. The actual area must be somewhere in between those two. So really, the sided sums are just a way to say, hey, we can't calculate this exactly, but we can do the best we can with one of them being too large and one of them being too small. I should be careful with saying that because sometimes you don't have over and underestimates, but I'm going to get to that in a second. But essentially, the reason there's these two different types is just they give us two different estimates. And it's just a way to get a better idea because you have a better understanding of it's probably between these two numbers that you're given. I don't know if that was helpful at all, Kayla, but hopefully it'll click in a couple more examples. Really, the point is we're doing this because they're telling us to. It's the way we have to estimate these areas at this point in time. And yeah, I also struggle with my right from my left. You know, I do this a lot. I'm like, okay. But anyway, the other thing I have to talk about really quick before on is this thing that I wrote up here, the N and the delta T. In terms of, okay, so not your homework that's up right now because that's still chapter 4 material, but your homework that'll be coming up next week when we actually have homework on this stuff. You're going to see a lot of things like what is N, what is delta T. This can also be a delta X. It can be a delta whatever variable you're working with. And the N is going to be the number of rectangles. So in this case, the N value would have been 5 because we ended up with 5 rectangles. And then the delta T is going to be the width of the rectangles. So in this case, it would have been 2 rectangles. Can't spell. Rectangles. Rectangle. Now I just feel like I'm not spelling it right. Anyway, rectangles, however you spell rectangles. So in this case, our delta T value would have been 2. So if you're doing your homework next week and you see like what is N, what is delta T, that's what they mean by those. And sometimes I don't know if we'll get to it today, but there's an example at the end of these notes where it essentially tells us what the delta T is. And that's kind of what I was saying before, where sometimes they tell us how to form the rectangles and sometimes they don't. Sometimes they tell us break this interval into 5 rectangles, or they tell us break this up into rectangles of width 2, and then we have to do it correctly. So sometimes they specify, sometimes they don't. If they don't specify, you kind of get to choose. If they do specify, then of course you got to do the one they specify for. Anyway. Do I want to talk about that or do I want to leave that? And let's just leave that for now. We'll get to that in a second. Any more questions on this? How I got any of those? Okay. So let's do, well, we got a tiny bit of like note stuff and then we'll do a few more examples until the end of class. So in some situations, but not all, we can look to find an overestimation, or an underestimation. Which will provide a too large or a too small estimate respectively. A function must be purely increasing or purely decreasing on the interval in question for these specifications to hold. What I mean by that is, let me draw a couple of pictures. So we kind of have 4 situations. So 1, 2, 3, 4. you could have, well, and they don't need to look exactly like this. It's just like you have an increasing option and a decreasing option. And we have two situations for each one. So the first and third are just some kind of increasing function, and the second and the fourth is some kind of decreasing function. So my right hand was in the blue. Okay. So say I want to do a right hand estimate, right hand sum, which I usually abbreviate with RHS, right hand sum. So if I was doing a right hand sum for this, and say I was breaking it up, you know, in just 4 pieces or something, I would essentially be taking rectangles that look like this. So notice if I take a right-hand sum of this increasing function, I get an overestimate. And I'll try to go through these semi-slowly in case y'all are trying to keep up with me. If I do a right-hand sum on the decreasing one, though, and I still try to break it up into 4 pieces, whoops, and I go, oh my lord, stop it. Go up to the right, most endpoint, right, right. And then this one's actually kind of just on the ground, if you will. Notice that when my function changes to decreasing, the right-hand side changes to be an underestimate. So I want to be really clear that it's not a relationship between the right and the left that gets you an over and an under. It depends on whether the function is increasing or decreasing. Because then what if we do left-hand sums? So left hand on both of these. If we do left hand and we break it up into 4 pieces again. So we go up to the left point and over and down, and up to the left point and over and down, and up to the left point. And imagine these rectangles were actually the same size in width. They're obviously not, but that's because I'm doing these very kind of quickly and not actually trying to make them look nice. So when I now change to doing a left-hand sum, essentially the classifications for over and under switch. A left-hand estimation on an increasing function is going to be an underestimate. And a left-hand sum on a decreasing function is going to be an overestimate. Now, I'll babble a little bit while y'all might be catching up to draw those. Your book and Wiley really likes to use overestimates and underestimates instead of right-hand side and left-hand side. I'm not a big fan of that. I always prefer to make my specifications in terms of left-hand side and right-hand side. Because again, there's also the situation where you can't always call it an over or an underestimation, and I'll do an example of that in a second. So when I write a problem, I will always specify right-hand side or left-hand side. But just know that in terms of your book and Wiley, sometimes they'll say, find an underestimate, and then you have to figure out whether it's an over or an under. What you would do then is you would figure out if the function's increasing or decreasing and kind of come back to this, you can almost seriously come back to this picture and say, okay, well, if I found out it's an increasing function, they want an overestimate, I need a right-hand side. But again, in terms of me, I will always specify right versus left instead of over versus under. The only thing I will ever ask for in terms of over and under estimations is I usually ask a type of question where I give you a bunch of graph options and they have all their Riemann sums on them, so they have all the rectangles drawn out, and I say, pick which one of these is an overestimate, and you have to tell me which one is an overestimate. So for me, that's the only really thing you need to pull from over and under is understanding which one's which. Like if you have the drawing in front of your face, can you tell if it's an overestimate or an underestimate? Now, again, in general, sometimes you can't tell whether it's an over and underestimation. Let me try to like squeeze this in down here really quick. So say if you have a function, you know, kind of like the one we started with originally, but a little more pronounced. If I do a right-hand sum on this, I don't know, let's just split it up into a bunch of pieces. If I do a right-hand sum, so I use all my right endpoints for my y values. Notice in that situation, I have that first rectangle and that last rectangle that are overestimating. The second and third rectangle are underestimating, and that fourth rectangle is kind of doing a tiny little bit of both. So if the function is not purely increasing or purely decreasing, I can't tell what this is. The only thing I can say is I can call it a right-hand side sum. Right-hand sum, a right-hand side sum, whatever floats your boat. But I can't say whether it's an over or an underestimation just by looking at it, because I don't know if it's overestimating more or underestimating more. Just saying overestimate or underestimate, it kind of has to be really, really clear, and it can only be clear if it's purely increasing or purely decreasing. But again, in terms of questions I will ask you, the only thing you really need to understand is looking at a picture and telling whether it's over or under, but just be slightly careful because Wiley can ask you for over and underestimations, then you kind of have to think about which side sum it is. Anyway, so let's do another example. So the chapter 4 homework is due on Monday. So the homework that's up right now is due on the 2nd. And then your next homework will appear on the 2nd, and that will be this stuff. So there's no homework on this stuff yet. That stuff will appear on Monday. You have the chapter 4 homework that's due on Monday, the 2nd of November. We're already in November, almost. Lord Almighty. All right, let's do another example. So this is another table example, but notice that we're no longer talking about velocity. So we don't need to talk about velocity. The only thing we really, well, we don't need it, but the thing that usually happens is we'll be given a rate, and we want to find the area underneath of that rate function. So that's why it gives us here the rate of sales in games per week of a new video game is shown in the following table. Assume that the rate of sales increased throughout the 20-week period. Estimate the total number of games sold during this period. So essentially the point is you're going to be given a rate, and then you're going to be asked for like a total change in whatever that rate is for. So since this is for a rate in sales, they're going to ask us for a total amount of sales. So when you're given a rate and you're asked for a total amount, you should think area underneath of function thoughts. Now, again, here, they didn't tell us anything about how to break up our interval, what kind of rectangles to use, how many, what widths they are, that kind of jazz. So we get to choose. Now, the best thing is to always choose as many rectangles as you can. So since we can break this up into pieces of like 5, 0 to 5, 5 to 10, 10 to 15, 15 to 20, let's go ahead and use 5 as our width, which will make 4 rectangles. Okay, so we're gonna, just to try to use the verbiage that I mentioned earlier, we're gonna let n be 4 and delta, there's no variable, but it's time, so I'll say delta t is 5. So we're gonna take the width of these intervals to be 5, which is gonna give us 4 rectangles. The other way you can think about it, especially in terms of your homework for next week, we're going from 0 to 20. And if we want to break it up into 4 pieces, 20 divided by 4 is 5. Or if you want to break the widths into 5, 20 divided by 5 is 4. So there is kind of that relationship between the total length of the interval and the number of rectangles and the width. But anyway. No, I don't want to say that. That'll be too confusing. So essentially we have these 4 intervals. We're going from 0 to 5, from 5 to 10, from 15 to 10 to 15, whoops. And from 15 to 20. This piece you don't necessarily need to do, but I find that it helps some people, so I'm going to write it down. So I essentially broke that table up into the kind of options we're going to have. So we have kind of those 4 intervals that we're working over. So let's find our right hand and our left hand sum. Again, they didn't specify, so really in general we would just need one of them, but since we're being super specific and we're doing as many examples of these as we can, let's do both. Oops. What the heck is that? Hopefully the green isn't too light. I probably should have chosen a darker color. So right hand side. Nope, bring the color back. So right hand side, again, so we have these kind of intervals we're working over. So what are the y values we're going to use? We're going to use the y values associated with the right endpoint of all of these intervals, of all of our rectangles. So if our first rectangle goes from 0 to 5, we're going to use the height at 5. The second rectangle goes from 5 to 10, we're going to use the height at 10. Now the other thing, just for the sake of our handwriting, the n is just like, that's just generic notation to say number of rectangles. So I just
okay.
So I just kind of my mic stopped working. So since this is essentially breaking it into sections of 5, from 0 to 5, 5 to 10, 10 to 15, 15 to 20, that would have given us 4 rectangles. So I just said n equals 4 just to note, because your Wiley homework uses that notation a lot. So I just wanted to make sure that we're getting used to it a little bit. What was the other thing I was about to say? Oh yeah, for the sake of our handwriting, I mean, it's not too much, but when we get to large, notice that with these right and left hand sums, the width appears multiple times, but the width is the same in each piece. So like in the one we just did, the width was 2, so we were writing 2 times 2 times 2 times 2 times, so on and so forth. So if you don't want to write that width every single time, so if you think about it, all of those terms have a 2 in it, so you could factor it out to the front. So if you want, you can always write these as the width in the front and then just add up the lengths, because it'll be the same thing. So I'm going to do that here. If it freaks anybody out, let me know and I can do it the flat way. But essentially we have a width of 5 for all of our rectangles. So I can essentially write it on the very outside and now just sum up the lengths of the rectangles. Instead of saying 5 times plus 5 times plus 5 times plus 5, I'll just put the 5 on the outside. So what's the length of the first one? Well, it's the y value associated with 5, which is the right endpoint of our first interval. So 585 plus the width of the second rectangle, which is going to be the y value associated with the right point of the second interval. So y value at 10, 892. Plus the height of the third rectangle, which is at the right endpoint of the third interval, which is 10 to 15. So the y value at 15 is 1875. Plus the length of the fourth rectangle, which is the right endpoint of the fourth interval. The fourth interval is from 15 to 20, so our last length is going to be the y value at 20, so 2350. So if it helps you to think about this in terms of like actual intervals and then thinking about the right side and the left side of the interval, think of it that way. If you can think about it without having to break it up into those intervals, go right ahead. If we punch that into a calculator, 28,510. That's a 5. And this would be in games. Because if the rate is in games per week, then the area is just going to be essentially like the numerator of the rate. So just like when we were working with velocity, the miles per hour turned into miles and the feet per second turned into feet. Here we have games per week, which is going to turn into games. Let me move up this really quick because I'm going to want to write something underneath that. Is everyone okay with how I found and used all of those numbers? Give you like 5 seconds. Okay. Now with the left-hand sum, the width isn't going to change. These are still going to be intervals of width 5, rectangles of width 5. And again, instead of writing 5 times, 5 times, 5 times, 5 times, I'm just going to put it on the outside. So what lengths am I using? Well, now I'm using the left side of kind of the intervals that I'm splitting this into, you know, kind of the sides of the rectangle. I'm going to use the left side of the rectangle for its height. So the length is going to come from the y value at 0, so we'll have 0 for our first rectangle. Then our second rectangle extends from 5 to 10, so we'll use the y value at 5, so 585. Third rectangle extends from 10 to 15, so we use the left endpoint of 10, which gives us 892. Our final rectangle extends from 15 to 20, so we'll use the y value at the left endpoint at 15, so 1875. This will give us 16,760 games. Now, that's all fine and dandy. We have a right-hand sum and a left-hand sum, and because this is increasing, so we have some kind of increasing function. So sorry, I always have to remind myself in my brain. So the left hand is going to be the under, and the right side is going to be the over. It didn't really specify us figuring that out, but just to put that in there for giggles. But what if we wanted like just one estimate? Well, if we wanted kind of a better estimate, so kind of the best estimate we can get here, would be to average the two. And just note that that is something that you might have to do on your Wiley homework when the chapter 5 homework appears. They might ask you to, I forget, and I also haven't written the, well, put together. I don't write the problems together that homework set yet. So I'll try to look through it before I post it. But sometimes they'll want you to average the two to get a better estimate. So the better estimate is the average of those two, which is 22,635. If I ever want you to average, I will say something like find the best estimate, or actually say find the two-sided sums and average them. I'll be super specific if I want that one. Otherwise, just read the instructions for which side I ask you to do, or I'll tell you what sums I want you to find. Questions, concerns on that before I don't think we'll finish the next one, but I at least want to start it because it's a slightly different format. But I'll wait a couple more seconds in case there's more questions on this one. Okay, not seeing any, so I'm gonna scroll. Maybe I'll try to leave that in there for a couple more seconds. So say we want to look at this one. So if T is an hour since the start of a 20-hour period, a bacteria population increases at a rate given by 3.0.1 T squared. Make an underestimate of the total change in the number of bacteria over this period using delta T equals 4, then delta T equals 2. And I actually meant to not put delta T equals 1 because that's too obnoxious of one. So we're just going to talk about that one later and not actually find it. So we'll talk about it when we get to it. Again, that might end up being on Monday. But we'll talk about it, but we won't calculate it because that would be adding up 20 things, and that's too many. So this is different because we don't actually have the values yet. We're given a function, we aren't given a table. And you can find a table, which is actually what I'm going to do. You don't have to find the table if you just want to list the values, but I'm going to go ahead and find the table. Now, I'm going to be very specific in my table because I'm going to make the table so that I can do both of the problems from that same table. Let me move this down a little bit. I was writing very crooked. So notice that we're working over a 20-hour period, but then it's telling us how to break up the widths of the rectangles. So if we have a 20-hour period and we're breaking it up into widths of 4, that's going to mean that we're going to have 5 rectangles. 20 divided by 4 is 5. So we're going to have 5 rectangles there with widths of 4. And then if we do the next one where we're going to want delta t to be 2, well, 20 divided by 2 is 10, so we're going to have 10 rectangles there. And I believe I am correct in saying for myself that I will never ask you to find a Riemann sum with more than 10 things, which is why we're just going to talk about the third one instead of actually doing it, because that would be 20 rectangles, and that's just gross. Now, we're going on a 20-hour period, so we're going to go from 0 to 20. So if we need delta t to be 4, that would be things like 0 to 4, 4 to 8, 8 to 12, 12 to 16, 16 to 20. So we'll need those values. We'll need the values at 0, 4, 8, 12, 16, and 20. But if we're then going to need delta t equals 2, then we're going to need 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So why don't I go ahead and so notice that the delta 2 ones kind of overlapped the delta t ones. So delta t included 4, and so did the delta 2. So why don't we just go ahead and find all of those values: 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And this would be a really great spot to use that table feature on your calculator. We might not even have time to do one of these, but we're going to keep going until we run out of time. So the function we're using is this 3 plus 0.1 t squared. So we're going to need to find all of those values for that function. So again, if you were doing this by yourself, I would suggest just doing it in that, you put y equals key and then you plug in the function 3 plus 0.1. You need to make it x squared on your calculator and then do the second graph to get the table if you have a TI-84 or 83, because that'll make your life easier instead of 10 times. But for the sake of time, I'm just going to tell us what these values are. So we've got 3, 3.4, 4.6, 6.6, 9.4, 13, 17.4, 22.6, 28.6, 35.4, and 43. Now, we're asked for an underestimate, and I think we're only going to have time to do one of them, but we're asked for an underestimate. Now, is that a right-hand side or a left-hand side sum? Well, notice that these values on this function are increasing. So we have an increasing function, so then an underestimate, you can kind of look back at those kind of drawings that I did earlier. For an increasing function, an underestimate, it's going to be a left side sum. So we're going to find left side sums. Again, I will always specify right versus left, but this is a problem directly from your book. That's why it says underestimate. So let's do this first one, and then we'll save 2, and we'll talk about part 3 on Monday. We'll save 2 and 3 for Monday. But let's do part 1. So part 1 is delta t equals 4. So we are having our 5 rectangles. So, and this is another thing that can happen with some table examples as well. So say we were already given this table, sometimes you don't use all of them. So notice with delta t being 4, we're only looking at 0, 4, 8, 12, 16, and 20. So we're not using all of the values on this table. We'll use it for number 2, but we're not using all of them for number 1. We're only using the values, we're only considering the values at 0, 4, 8, 12, 16, and 20, because those are what gives us our delta 4. Do this in case people like the, so essentially we're going from 0 to 4, from 4 to 8, 8 to 12, 12 to 16, and 16 to 20, in case people like this kind of interval notation thought process. So we're using a left-hand sum. So we're going to take the y values from 0, 4, 8, 12, and 16. So the width of all of our rectangles was 4. So we're going to have 4 times all of our lengths. So I'm just going to put 4 on the outside. What's our first length? It's going to be the length at 0, so 3. And then the length at 4, so 4.6. Length at 8, so 9.4. Length at 12, so 17.4. And length at 16, so 28.6. And yes, these questions are tedious, in case you're thinking that. So we used, you know, the left-hand endpoints to get us all of our, you know, kind of y value lengths for our rectangles. Oh Lord, this is this one. Okay, this will give us 252 if you were to plug that into a calculator. So we'll start with the next one next time. I know we have 3 minutes, but I honestly would rather just do it as a review next time to remind us what we're working with. So we'll talk about 2 and 3 on Monday. But this is essentially 5-1. We're essentially done 5-1. This is the last example for 5-1. So in 5-1, what we're doing is we're doing these Riemann sums, which are taking these rectangles, adding all of their areas up to estimate the area underneath of a function that might not have a very nice shape to it. We're going to use these later. And again, I think I mentioned this, maybe I just mentioned it to my other class. Kind of like with derivatives, what we're doing is we're building up the kind of process behind it, and then we're going to kind of, just like we did instantaneous rate of change and then jump to actual derivative rules, we're going to have a similar thing here. We're doing Riemann sums, and then we're going to jump to these things called antiderivatives. How did you get 3.4, etc. from plugging in the equation? You get 3. Oh, did I? 3 plus 0.1 x squared. So I see 3.9 when I plug in 3. Let's see. 3 plus 0.1 times 2 squared gives me 3.4. Are you plugging in 2 or 3? Let me. If you don't have any questions here, feel free to go. But let me 1 second, Kayla. Let me pull this up. Where'd it go? Oh, can you move? Why are you plugging in 3 if we want to find it when we plug in 2? Still trying to pull this up, by the way. Okay. So yeah, we wanted to find 0, 2, 4, 6, 8, 10. We wanted all like the even numbers, so we weren't plugging in 3 or 5 or 7 or any of that jazz. So maybe that's what was. Because yeah, I agree. When you plug in 3, you get 3.9, but we don't need 3 here, so we didn't find it. But I guess hopefully that was just, then I'll stop pulling this thing up. And okay, cool. So yeah, the reason, just one last thing, Kayla, the reason we didn't need 3, 5, 7, 9, etc. Is because of the intervals that we're looking over. So in part 1, we're looking in groups of 4, so 0 to 4, 4 to 8, 8 to 12, 12 to 16. And then the second one, which we haven't done fully yet, and the second one we want to look at intervals of 2, so 0 to 2, 2 to 4, 4 to 6, 6 to 8, and so on. So we never had any of the odd numbers showing up because we were looking over even intervals. If we were to do the third one out fully, which again, we're not going to do, but if we were to do the third one out fully, that would be an interval of 1. So we would have seen 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. So in the delta t equals 1 case, we would have needed f of 3, f of 5, f of 7, and all those. But since we're working over even intervals, we didn't. Anyway. If anybody else has any questions, feel free to ask them. Otherwise, have a great weekend. Have a great spooky day on tomorrow. And I'll see you on Monday.